So what is a VPN and why do we need it? Well, a VPN, in case you've never seen that acronym before, stands for a virtual private network. So let's break this down a little bit. What do we mean by a virtual network? Virtual network strictly is used in the context that in order to connect two or more of your networks together, so two or more of the networks that you control, that you've cabled, you've set up the routers and switches and everything, they are yours, we need to make use of someone else's network. Typically this would be like a service provider's network. So we're leasing or renting another's network to connect our network together. And what makes it a virtual network is that from the perspective of our routers and switches in our networks, there's nothing that they really know that makes it apparent that the network in between is someone else's network. There's nothing special we have to configure to make them think that they're connected to a non-company network. Routers and switches think they're connected end to end. They don't know there's actually another network in the middle that's transporting packets back and forth as a service to us. And that is the virtual part of the network. Now, what makes it private? Well, in a VPN, as it says here, privacy is typically attained via route privacy. In other words, if I send a routing update into that virtual network, if I send an OSPF or an EIGRP update, well, that service provider's network that I'm using, that I'm renting, is probably also being used by my competitors and other people as well. And if I'm sending routing updates into it, I want to make sure that my routing updates are not seen by any of the other people that service provider is renting it to. So in other words, if my competitors are using that exact same service provider's virtual network, when I send an EIGRP or an OSPF update into that network, I want to make sure it pops out on the other side only at my network, at my remote office or my headquarters. There's no way I want my EIGRP or OSPF routing updates when it enters that virtual network to pop out at the customer at a competitor's router or somebody else's router. So it's up to the person who's providing that virtual network to me to make sure that any routes I inject into it are kept isolated and independent just for me, that they're not mixed up or confused with another customer's routes. Another aspect of the privacy that you get in a virtual private network is probably what most people think of, which is your data privacy. In other words, as I send actual packets into that network, like web browsing, people trying to get from a remote office to the central site via the email or some sort of FTP file transfer or something, we want to make sure that, number one, those packets go where they're supposed to go. So for example, if someone in a remote office is trying to connect via email to the email server in the headquarters, we better make sure that VPN does not misdirect or redirect that email request to a competitor's network or some other customer's network. It's got to stay within my VPN. And similarly, as my packets are traveling through that VPN, we also want to make sure that if for some reason someone is able to intercept those packets, they shouldn't be able to make any sense of what they're seeing. In other words, we want to encrypt those packets. As the packets enter the VPN, we want to encrypt them so that anyone who's looking at them won't be able to make any sense out of them. They'll just look like meaningless garbage to them because they won't have any method of decrypting those packets. Sort of like we're using a secret code to encrypt our data as it goes through the VPN. Now, VPNs don't have to do encryption. Mostly we think of it that way. Usually when I say, oh, I've got a VPN between this device and this other device, normally the first thing that comes to your mind is, oh, okay, we're doing encryption. You don't have to. Encryption is an optional part of a VPN. It is commonly used, but it doesn't have to be there. Okay, so for example, take a look at this. Before VPNs existed, I have 4 spokes. You know, these might be 4 grocery stores, and they all have internet connectivity, so they can browse the internet, and the employees at those stores can do their banking and everything. And there's also a hub location, which is the central office, the headquarters for my grocery chain. And now I have a desire to say, well, I want to connect these spokes to this hub. I want to transfer data back and forth, like, the day's sales and downloads of coupons and things like that to each one of these spokes. But I want to make sure that is secure. Well, before VPNs existed, how did you do that? Well, each spoke would most likely have to have some sort of a point-to-point connection into the hub. And if the spokes and that point-to-point connection could be PPP or frame relay or T1, but at the headquarters, I had to pay for each one of those monthly connection bills for those 4 different spokes there. Imagine if I had 400 spokes, how expensive that would be. So now, as the corporate headquarters, not only am I paying to have my internet connectivity, I'm also paying to have this private point-to-point connectivity from each spoke into the hub. And what if I want the spokes to be able to talk directly to each other? Well, then I have to pay for additional point-to-point connections between the spokes. So imagine if each one of these black lines here was represented by a T1 connection. That's a lot of T1s we're paying a monthly bill on to get our privacy. And then most likely also we would configure IPsec across these point-to-point connections. It's probably unlikely that anyone's able to sniff these connections and see our data, but if someone happens to sneak into the telephone company's office and manage to capture my packets as they go across these T1s, I'm going to want to encrypt them so people can't see what I'm doing. So that means each one of these routers would have to have a separate IPsec security policy for each connection. So right now, for example, router 1, spoke 1, he'd have 4 point-to-point connections and 4 IPsec configurations. 1 separate IPsec configuration, or what we call a security association, to each end of the point-to-point connection. That gets kind of cumbersome to configure that. Well, once VPNs were created, remember VPN is the concept of I'm going to use someone else's network to securely transfer data from one point to another. Well, hey, if I've already got an internet connection, why not use that exact same internet connection for my VPNs? So in this particular case, if someone in grocery store number 1, so maybe that's right here, grocery store number 1, if there's a computer or laptop right here that's surfing the internet, well, when it sends its data to spoke number 1, it'll just go out unencrypted as a regular IP packet to the internet, and he'll be able to go to ine.com or google.com or whatever. But if that same laptop in that grocery store is trying to upload, the day's sales, well, then in that case, when it goes to spoke number 1, it will get encrypted and go across this encrypted tunnel to the hub. Still physically using the exact same interface we use to get to the internet, still going through the internet. The main difference is one packet is clear text, unencrypted for anybody to see. The other packet going across the VPN is being encrypted into an IPsec tunnel. And this is the beauty of VPNs. We can have one physical connection giving us connectivity to a network, and we can have some encrypted and some unencrypted packets going across that common infrastructure. Now we're going to get into a whole bunch of terminology and stuff that you need to be familiar with, so let's just dive into it. At a very high level, VPNs come into basically 2 different flavors. You've got peer-to-peer and overlay. Peer-to-peer and overlay. So the first one, peer-to-peer. What that means is that your router right here, and by the way, the routers here on the customer's premises in VPN terminology are typically called CE routers, or customer edge routers, because they're at the edge of the customer's edge of the customer's network. And the other router at the other end of the connection that's at the edge of the service provider's network, well, you can probably guess what that is. That is a PE router, a provider edge router. Now, in a peer-to-peer VPN, that means that you've actually got some routing. It could be EIGRP, OSPF, BGP, but whatever the routing is, your CE router is forming a routing relationship with the PE router. So here on spoke number 1, if we did show IP OSPF neighbor or show IP EIGRP neighbor, our neighbor would be this service provider's router. So we form a neighbor relationship with that router, and then we send all of our local LAN routes to the PE router. And then the PE routers amongst themselves are probably running BGP or something. They send the routes here, and then this PE router has a routing relationship with the hub. So our peers are actually the service provider. The service provider is considered a layer 3 peer to our customer edge routers. Now, a couple things you need to be familiar with a peer-to-peer VPN. Number one, you're probably not going to be in charge of which routing protocol is run between you and the service provider. The service provider is most likely going to dictate that to you. So when you call up your service provider and you say, hey, I want a peer-to-peer VPN with you, they'll probably say, okay, well, you need to run OSPF with us, or you need to run EIGRP with us. And it's not a negotiation. For whatever reason, they've got their own policy in place that says they're running a certain routing protocol with the customers, and that's the routing protocol that you have to run if you want to exchange routes with them. So you lose a little bit of freedom as far as what routing protocols you can run to the service provider. Other thing to keep in mind is, now that my routes have been given to the service provider, they are responsible for exchanging those routes with the other service provider routers. I don't know what routing protocol they're using here in this cloud. Could be BGP, could be whatever, but I need to trust that there's some routing going on here in this cloud, that routing is configured correctly. I need to trust that when I send my routes to the service provider, it's not going to accidentally leave this way and go to a competitor's router. That would be bad. I'm trusting that they've got this all set up so that when I send routes to them, their routing will correctly forward those routes on only to other routers in my company. So the SP is responsible for exchanging my routes with other SP routers and keeping those routes secure. So those are some characteristics of a peer-to-peer network. Well, what other choice do I have? Well, another choice would be something called, if I can get to it here, an overlay VPN. In an overlay VPN, the service provider is providing me my physical layer and my data link layer connectivity. So, they might be providing me a T1 at the physical layer, and maybe I'm running PPP or frame relay across that, but they're not doing anything at the network layer. So from layer 3 on up, they say that's not our responsibility, that's your responsibility. So from a layer 3 perspective, I am overlaying my routing. So in other words, my routing is happening, my peers now are my own routers. So in spoke number 1, if I did show IP OSPF neighbor or show IP EIGRP neighbor, I would see that the neighbor was the hub. I wouldn't actually, from a layer 3 perspective, I would not see any routers or devices here owned by the service provider as peers of mine. My layer 3 routing is overlaying or sitting on top of whatever layer 1/layer 2 connectivity the service provider is giving me. And that's why they call this an overlay VPN. A lot of times you'll see these are also called layer 2 VPNs. Like if you go on to pursue something called MPLS VPNs, there's something called layer 3 MPLS VPNs and layer 2 MPLS VPNs. A layer 2 MPLS VPN would be like this. It's an overlay. Layer 3 would be a peer-to-peer VPN. So in this particular case, the responsibility has now been shifted to me to make sure that all of my routing is correct end to end. I still have my privacy provided by layer 1 and layer 2, right? If the service provider has done their job and they've set up my, let's say, frame relay circuits correctly, then spoke 1, when he sends data into the frame relay connection, it should only go to hub or only go to spoke 2. And when we get into the video on an overview of DMVPN, DMVPN is also an example of an overlay VPN technology. So, regardless of whether I choose a peer-to-peer or an overlay VPN, there's basically 3 common expectations of what that VPN will provide to me. Number 1, route exchange privacy. And I talked about this already. In other words, there's no way that when I send an IP routing update across this VPN that my routes will be mixed with those of my competitors. I don't know if you've seen it or not yet. I'm not sure what order you're watching these videos, but if you watch the video on VRF Lite, that's one example of a way to achieve this. VRFs are one feature that can be used by the service provider to make sure that the routes are separated from each other, that the routes I send to that service provider are isolated and are not commingled with routes sent from another customer or possibly a competitor. Another expectation of a VPN is path determination. Packets sent from my company will never accidentally arrive on the interface of one of my competitors' routers. That's something else that the VPN should provide. And lastly, data security. If anyone outside of my company ever intercepts my packets, which should not happen, I don't want them to be able to read, change, or replay those packets. Now the first two items, route exchange privacy and path determination for packets, that's typically dependent on what type of VPN you select. You know, are you selecting DM VPN? Are you selecting GRE? Are you doing some sort of IPv6 tunneling? So the type of VPN you select will have built into it the first two items. Data security is typically provided by IPsec. And that brings us into our next topic, IPsec. Short for IP security, and it's a collection. It's sort of an umbrella of standardized protocols that provide, as you can see here, confidentiality, integrity, authentication, and anti-replay. What is all that? All right, let's go through each one of these bullets. Confidentiality. This is saying encryption, right? And confidentiality means if someone else happens to intercept my packet in a sniffer or Wireshark or something, they won't be able to tell anything about it. It'll just look like gobbledygook to them, like it's all hashed together, and they won't be able to tell if I'm trying to do banking or web browsing. There's no way to tell what that packet is. Integrity is verifying that the packet has not been modified in transit. And it wouldn't be nice if my company, when they're depositing my paycheck into my bank account electronically, you know, maybe they're only depositing a $100 paycheck. Wouldn't it be nice if I could intercept that, and if I knew exactly which bytes to modify so I could make that $100 paycheck turn into a $10,000 paycheck? Well, integrity prevents that. Integrity makes sure that, okay, there's some way of making sure that when the data is received, it has not been changed in transit. An analogy of that is, think about Ethernet. Ethernet does this built into the protocol because Ethernet has an FCS value at the end of every single Ethernet frame that makes sure that when the receiver gets that Ethernet frame, the FCS can tell you if the frame has been modified or not. That's what integrity does, and IPsec has a collection of protocols that can do that for you. Authentication. When I establish a secure connection to my bank electronically, how do I really know it's my bank at the other end of that connection? I mean, yeah, the web page I pulled up looks like my bank's web page, but what assurances do I have that somebody hasn't spoofed that connection? I'm not actually seeing a web page that my neighbor dished up on their own internal network. So authentication is verifying that the other end of the connection is who they really say they are. And then anti-replay. This is, okay, what if someone happens to capture my packets? What's to prevent them from replaying those packets back into the network again? For example, let's say they capture as I'm trying to log into some device. You know, maybe I'm trying to log into my banking website and somebody happens to capture those packets. What's to prevent them from replaying it for their own session, pretending that they're me, so they can use my same username and password to log into that bank? Anti-replay prevents that. It says, look, when a packet's sent, you cannot copy it and resend it again. There's something in the protocol preventing that from happening. So IPsec is a collection of protocols. IPsec itself is not actually a protocol. It's a name of a collection of protocols that you can pick and choose to do one or all of these things right here. And there's a wide variety of RFCs. There's not just one RFC. If you type in Google or something, IPsec RFC, you'll see there's a whole collection of RFCs for doing these various different things right here. Main thing to know though is that IPsec is a standard way of doing this. So if I'm running IPsec on a Cisco router, I should be able to establish a secure connection to a non-Cisco router at the other side. I'm not using anybody's proprietary protocols when I'm doing IPsec. Okay, now within IPsec, some other terms we need to be familiar with. An SA stands for a security association. This is basically just a fancy way of saying I have a secure connection between my laptop and my banking website. If I'm using IPsec to create a secure encrypted connection between my laptop and my bank website, I have created a security association, an SA. IKE, no, it's not someone's name. It actually stands for Internet Key Exchange. As I'm sure you can imagine, most security protocols, especially any kind of security that involves encryption or hashing of some kind, uses passwords, right? CHAP uses passwords, all kinds of things use passwords. Well, in the context of IPsec, we actually don't call them passwords. We call them security keys or keys. And actually, they're massively long, complex numbers. Looks like a whole paragraph of nothing but meaningless numbers and letters all gobbled together, and that's what we call a key. So keys are used in a lot of things in IPsec. There's not just a single key that's used. And so when you're establishing an IPsec connection between two devices, these two devices have to have some way of dynamically deriving the keys that are going to be used and exchanging those keys between each other. And the Internet Key Exchange is the protocol that's used to do that. Now, when you're using the Internet Key Exchange, like for example, if you're doing this in a lab or something and you're starting out, well, you're probably going to just manually define your keys. Type in some real simple command to manually define the keys and the keys will be static. IKE can do that. Or IKE can be very horribly complex where it dynamically creates dynamic keys for you and changes those keys over time, and you get to configure how frequently do you want it to change the keys. So IKE, the Internet Key Exchange, is a critical component of IPsec. Now, IKE, if we drill down a little bit further into the Internet Key Exchange, has two primary phases you need to be familiar with, phase 1 and phase 2. And these two phases, the main objective is to set up a security association between two endpoints. So that's what we want. So let's say that I'm doing IPsec from one router to another. I don't really want to burden my laptops and my PCs with IPsec configuration. I want the routers to do that. Okay, well then router 1 has to set up a secure association, an SA, to router 2. First thing that's going to happen is IKE phase number 1. And here's another protocol you need to be familiar with. The Internet Key Exchange uses a protocol called ISA-KMP, the Internet Security Association and Key Management Protocol. Whew, that's a mouthful. Basically, ISA-KMP, I'm not sure if I'm pronouncing that correctly, but ISA-KMP is the fundamental root protocol within IKE to derive keys and exchange keys between two different endpoints. So in IKE phase 1, the primary intent or objective of phase 1 is to say, okay, me and router 1, so let's say I'm router 1, me and router 2, I know I'm going to need to form an IPsec tunnel connection to router 2. I know that when data comes into me, I'm going to need to encrypt it. So router 2 and myself, we're going to have to come up with some really complex encryption keys. But how do I exchange those encryption keys with router 2 in a secure way so that if someone's watching this and they see this exchange, they don't actually see the keys? Well, why don't I take a step in advance and create a secure tunnel in advance? And that's what IKE phase 1 is. Let me create a tunnel, encrypt that tunnel with a different set of keys, and once that initial phase 1 tunnel is complete, then I will exchange my encryption keys with the router 2, with the other endpoint. So that's what we mean by an exchange of transform sets. An exchange of transform sets is like where I say, hey, router 2, I'd like to do IPsec with you. Are you okay with that? Sure I am. Okay. All right, great. Let's see here. With IPsec, I've got a variety of different encryption protocols I could use. Here's the ones I support. What do you support? Oh, I support this, that, and the other thing. Okay, great. In addition to that, I'd like to do authentication. Here's some authentication protocols. So a transform set is the set of IPsec protocols that you support, that you're talking, that you want to see if the other end can support. Here's an analogy to this. I don't know if you've seen the videos on BGP yet, but if you haven't, this will be a little preview of this. So BGP, if you don't already know, is what we call multi-protocol BGP. In other words, BGP routers can exchange not only IPv4 routes with each other, but other things as well. IPv6 routes, multicast routes, all sorts of things. Well, when a BGP router is first sending a BGP open message to its peer, saying, hey, I'd like to talk BGP with you. In that open message, he says, here's the things I'm capable of. I'm capable of IPv4. I'm capable of IPv6. I'm capable of multicast. So in that initial exchange of open messages, they're exchanging their capabilities with each other and saying what they'd like to do, what types of information they'd like to exchange. Same type of thing is happening here in the world of IPsec in IKE Phase 1. I'm saying, hey, here's the authentication protocols I support, and here's my preferred one. Here's my encryption protocols I support, and here's my preferred one. And those are called transform sets, that set of standard protocols that you want to use, that you're trying to negotiate with your partner. So that is IKE Phase 1. And then we go on to proceed with IKE Phase 2. So IKE Phase 2 is where we actually create our unidirectional security associations between the tunnel endpoints. Now, what do I mean by unidirectional security associations? Well, in IKE Phase 1, there's one key that's used bidirectionally to form that tunnel. In other words, if I'm router 1 and you're router 2, we're both going to have the exact same key to set up this initial Phase 1 tunnel. It's a bidirectional tunnel that's using the same key in either direction. Once that tunnel is set up, now we're going to create unidirectional security associations. So the security association I have, the encrypted channel that I have from me to you, is going to use one set of keys. And then if you ever need to reply to me from you to me, well, that's a different direction. That's another unidirectional security association, and we'll use a different set of keys for that. And all of that is negotiated and set up in IKE Phase 2. So once these two phases of IKE are complete, now we're ready to actually take our users' web browsing traffic, email traffic, whatever, and encrypt it and send it across this tunnel. Now, let me take a step back there. I'm saying encrypt it. Like I said, encryption is optional. Maybe we're not doing encryption. Maybe all we're doing with the traffic is we're doing integrity and authentication with it. Or maybe anti-replay. But in reality, most people that use IPsec, they use it because they want the encryption functionality out of it. All right, a couple of additional terms for IPsec, AH and ESP. So AH is authentication header. And yes, here's another number you got to remember, IP protocol number 51, so that'll be in the IP header. And ESP is the encapsulating security payload, which is IP protocol number 50. So just based on the fact that these are IP protocol numbers gives you a little bit of a clue as to what's going on. Now, if you received an IP packet, and let's say it had an IP protocol number of 6 in the header, what does that mean that you can expect to see after that IP header? Another header that's TCP, right? Because IP protocol 6 is TCP. If I gave you an IP header with protocol number 17, you would expect to see a UDP header behind that. Now, in this particular case, if I hand you an IP packet that's got IP protocol 51 in it, now you can probably say, aha, that must mean there's another header after the IP header, but it's not TCP, it's not UDP, it's something called the authentication header. Or if that IP header contains IP protocol number 50, there's another header, but this is a different header used by a different protocol called the encapsulating security payload. So what are these used for? These are things that you configure. In your router, you would say, which one of these do you want to use in this particular security association? Do you want to use authentication header, encapsulating security payload, or you could actually use both in tandem. Both of them offer authentication and integrity. So you get those benefits no matter which one you select. But the main benefit of ESP is it gives you encryption. And for this reason, that's why most people select the encapsulating security payload when they're creating an IPsec channel. Because after all, you probably use IPsec because you want encryption. And authentication header is not going to give you that. Last section of this video, tunnel versus transport modes. Now, when you choose authentication header or encryption, an additional thing you'll have to select in your configuration is whether you want each one of those protocols to use transport mode or tunnel mode. So you're going to have to choose one over the other. Now, what's the difference between those? The main difference is this. As that IP packet gets put into that tunnel, or I should say gets handed to IPsec, once IPsec is done with it and then forwards the packet on into the network, do you want that original IP header of the packet exposed, or do you want it hidden? That's the main difference. Let's take a look. So if I'm using authentication header, and remember, this is just giving me authentication and integrity. I think it's also giving you anti-replay, but it's not giving you any kind of encryption. So what's happening here in transport mode? Well, as you can see, we're just taking, after the IP header, we're putting in an additional header called the authentication header. And the authentication header basically uses a variety of protocols against all these fields here, from the IP header all the way down to the data, so that when the receiver gets this packet, it can make sure that nothing's been changed, that it actually came from the correct source going to the correct destination, so that's the authentication part of it. So the authentication header allows all of that to happen. It's just an additional header. Now notice, in transport mode, our original IP header is left exposed. It's not changed in any way. Now, if I was using authentication header in something called tunnel mode, what that does is instead of my header being placed after the original IP header, now my header is placed before the IP header. So this is the original IP header right here, and we put a new IP header in front of it. So if you're familiar at all with tunnel interfaces, whether a tunnel interface is doing GRE or IPv6 tunneling or whatever, you know that the main concept of tunneling is that some data comes into my tunnel interface and I put a new header on the front of it and it pops out. So when it pops out, the original data is sort of hidden and there's a new header in the front. And that new header, the source of the new header is the router that just tunneled it, and the destination address of that header is the router at the other end of the tunnel. And once that tunneled packet gets to the other end of the tunnel, it's going to hit some other router, some other tunnel interface where that additional header will be stripped off, revealing the native packet inside so it can go along its way. Same kind of idea here. In tunnel mode, both with authentication header and encapsulating security payload, the concept is we're leaving our original IP header alone and we're putting some new headers in front of it. In this particular case, we're putting the authentication header in front of it and a brand new IP header in front of it. And this new IP header has a source of my router and a destination of the router or the security appliance at the other end of the tunnel. Lastly, just by comparison, if I was doing encryption with encapsulating security payload, it would look like this. So here with ESP in transport mode, my original IP header is left exposed, unchanged. I put an ESP header at the end after that. Now ESP also uses a trailer and a special ESP authentication field. And you can see here with ESP, if I do encryption, the data and the trailer are encrypted. Now that's if I'm doing transport mode. If I'm doing tunnel mode, now my original IP header is encrypted along with the data and the trailer. because I now have a new IP header to get this packet routed through the IPv4 network. A few other things I want to mention about this. Transport mode, the one where the header is exposed, is typically recommended when IPsec is run from peer to peer. So for example, if you were initiating the IPsec connection on your laptop and you were doing IPsec all the way to maybe a banking web server or something at the other end, then you would probably be using transport mode. Whether you're using authentication header or ESP, you'd be doing transport mode. Tunnel mode is typically used when the IPsec endpoints are network infrastructure devices, like both ends of the tunnel are routers, or both ends of the tunnel are specific security appliances or something like that. One other thing I want to mention is my very last point, is that these IPsec tunnels are typically dynamic in nature. In other words, one of the things you have to configure on the router, in addition to, what are all the different IPsec protocols I want to use, and do I want them to be tunnel or transport and all this other stuff, you also have to configure the router to know which packet is actually, what types of packets are actually going to use this tunnel. Maybe you only want FTP to be encrypted by IPsec, and all other traffic you just want to go out as is, untunneled, unencrypted. So the way these IPsec tunnels typically work is that they aren't even formed until interesting traffic is received by the router. And you get to define what's interesting. Maybe FTP is interesting to you. Maybe SMTP is interesting to you. But once interesting traffic is received by the router, then the IPsec tunnel comes up, the traffic is tunneled or sent across that security association, and then once that interesting traffic stops being received by the router, eventually some sort of aging or inactivity timer will expire and the IPsec tunnel will go down.